Hi and welcome to our presentation, Malt Yield Forecast for Bitburger, a toolbox for data-driven brewing optimization. This presentation was similarly held on the Predictive Analytics World Business. Today, Mina Shibata, research data scientist at RapidMiner, and Josef Kimberger, project engineer for data mining at Bitburger, will present our data mining journey in the beer brewing business, from data acquisition to deployment. We will also present our so-called toolbox that accompanies and encourages the brewer him or herself to take this journey. We will showcase this on a specific use case, the malt yield forecast. What is malt? Malt is grain that has been briefly soaked in water and dried again, and this activates enzymes in the grain which are necessary for brewing beer. This work was done within a research project called DAPRO, which is short for Data-Driven Process Optimization using machine learning in the beverage industry. Our project partners representing the beverage industry are beer breweries, Augustina and Bitburger. So we have this sophisticated product beer where the knowledge behind evolved over millennia and is now put into this industrial context with an increasing demand of resource-saving efficiency. This leads to new challenges. We want to maintain the evolved sophistication and the quality of the beer, but at the same time, we want to offer the customer a low price, and also we want to be more sustainable. We're confronted with many new problems. We have more and more unpredictable climate affecting the crop, so timing, quantity, and quality of the ingredients needed. And we have increasing prices of all kinds of resources, such as the ingredients themselves and energy. In addition, more resource-efficient behavior is again important in terms of sustainability in the fight against climate change, so against an increasingly unpredictable world. So in the end, we want to offer a good, tasty beer with a good price. Meanwhile, we have this traditional industry, which is already well digitalized and is already collecting huge amounts of data, where we think a lot of potential is still unused. This potential is what we want to unleash with our so-called toolbox. We believe that we need to make data science easy and more accessible for those who will ultimately use it and make decisions in production. So, the brewer, him or herself. So, the toolbox should reduce the effort needed to generate insights hidden in the already collected data. It enables the brewer with user-friendly access to more easily create analytical processes, to gain resource efficiency, to reduce downtimes in their bottling line, and maybe discover new knowledge connected with complex biochemical processes which are still not fully understood. Okay, let's put this into some context. At the very beginning of our project, we did some AI assessment. So we interviewed all the domain experts across the process line of beer brewing. So you can see here an overview of the process line from raw ingredients to beer in bottles and to logistics of the beer crates finding their way to the supermarket. And we identified many use cases, and those 7 you can see here are those we thought of being most interesting for us. But today is about the malt yield optimization, so let's focus on that. And this is the point where I would like to hand over to our brewing expert, Josef. He will tell us more about it.
Thanks, Mina. It's a pleasure for me to introduce you to our use case for optimizing our malt yield. So let me start with our baseline problems. We always have to adapt our processes due to the fluctuation in quality of our raw materials. A tough challenge for us is our malt silo management. We have a constant in and output, and it's very difficult tracking deliveries into production. Thus, we only have the possibility to react but not to act right when production starts. We also see the possibility to increase efficiency, to lower costs in raw materials such as malt. And we talk about huge quantities, which always need to be right available in time, so malt purchasement is made by purchasing departments with huge contracts. Malt yield is an important secondary KPI. This is why we want to check if we see a chance for a paradigm shift in production and maybe later also in production planning and purchasement. Our main goal of this use case is the prediction of the malt yield, which describes the efficiency of the process regarding our input parameters. The benefits would be the possibilities for brewmasters to act and not only to react and maximize the outcome of the brewing process. So, what is the brewing process? Let me go over the process real quick. The start is always when we get our malt deliveries and the storage of the malt. After that, we take malt in a certain mixture from our 14 silos and grind them in a mill. This coarse malt material is transferred in a vessel and mixed with water. Heated up, and we keep certain temperature levels to let natural enzymes degrade the starch and proteins into low molecular substances. For us, especially the starch is important since we need fermentable sugars, and the sugar content is important for our malt yield. Basically, we want to maximize the degradation economically. Next is the lautering process, which means we need to separate solid and liquid substances. So it's basically a huge sieve with the exception that we use our solid materials, the spent grains, as a natural filtration layer. The liquid, which is called wort, is transferred into the wort pan. Here it's important to maximize the separation for a good yield. That's why we wash the spent grains with lots of brewing water. After the lautering, we need to boil our wort. We add hops and set our final gravity by vaporizing water. In the end, we clarify the finished wort in the whirlpool, cool it down, and then we are finished. This whole process takes roughly 5 to 6 hours, and it's highly automated, and we collect tons of data along the way for every batch. So which data do we collect in our brew house? We have our malt specifications, we have silo information, we have process parameters, our production data, and we have lab results. And in the lab, we also calculate our malt yield. This is why it would be very handy if we could get the malt yield as soon as possible in our process, and even better, if we could predict the malt yield right at the moment when we set the mixing ratio of the malt at the start of the batch. Our biggest challenge is definitely our silo management, since we somehow need to know when which delivery finally ends up in a brewing batch. And that's the moment when I hand back over to you, Mina.
Thanks, Josef. So, what's a data scientist's perspective on this? Let's recap some data science basics. So, how does a data mining journey roughly looks like to get your model into production? So, we start with our raw data, where we already did some exploration and identification, so we already have knowledge exchange with the domain experts there. Then we do our data pre-processing and data engineering, which is customized to the specific use case. And then we have our process data and start with our model building based on that. All this is not a straight line. You always have iterative steps and back and forth and a lot of knowledge exchange between data scientists and domain expert here. This might take some time. But then once your data science is done, so you know which data you need, where your data is and what your model can predict, the next big step is getting your model into production. So you have built many prototypes and then the best suited to the use case to make your first predictions, and then we do evaluation of the model and the results and share and discuss with all the stakeholders to evaluate also if this is a model which has a positive business impact. So we can eventually set up our model for deployment, so we have some interaction with IT and DevOps there. And also here, it's not a straight line. We also have to monitor our deployed model if it's still current. And also here, we have always back and forth and iterative processes in between. So why did we visualize the data mining process as a line instead of a cycle? In CRISP-PM, as some of you might know, this is the chosen visualization because it's much clearer afterwards which the points of attack are of our toolbox. And for our toolbox, it's the brewer's point of view which is important for us. So how does a brewer see this and what might be his questions if he asks himself or herself, how can I solve problems or gain process insights using my data? So then he or she might ask, which data do I need? Where do I find it? What analysis methods are available? Which one is best suited for my problem? Or what are the results telling me? And how can I check if the results make sense? And can I use the model for my benefit and how? And then we want to help with our toolbox to answer all those questions. The Brewer's Toolbox comprises several components, where the heart of it is the so-called problem catalog. And there are several other assisting components, which are the data aid, analysis configurator, validation assistant, deployment manager, and the model understanding wizard. Let's take a closer look into the problem catalog, which is a selection of several use case modules which are infused with all the knowledge and insights gained during the iterative process and exchange between data scientist and domain expert. We want to make the knowledge easily recyclable for others, of course without leaking any sensitive information. So the brewer who did not take this data science journey before can choose a specific use case or similar use case from this selection. It replaces the first steps in the data mining process and reduces the iteration loops such that the brewmaster without deep data science knowledge can get the data mining journey rolling. While the use case modules contain all the requirements, the assistant components support to fulfill those. So the data aid helps you to find the right data. For the malt yield optimization, it would be the malt specifications, the information, and the lab results. and it also helps you to make the right transformations to prepare it for the analysis modules. The analysis module wizard then helps you to adapt your analysis modules to your current problem and to your current environment. Once all the requirements are fulfilled for the use case module, you can make your first predictions, and the model understanding wizard helps you to understand and interpret the analysis model in relation to the process behavior. Then the validation assistant helps you to consider all the several aspects of performance. Each will have its own metrics and measurements. It helps with the creation and application of meaningfulness tests and fully automate the detection of changes. It helps actively tracking and monitoring the model state, and then the deployment manager can warn you in cases of model performance deprecation or decay, bias creep, or even data skew and drift. If the model falls below an acceptable performance threshold, then a new process to retrain the model is initiated and that newly trained model is deployed. Managing deployed models and keeping track of which model file and configuration parameter set is currently deployed in production is the job of the deployment manager. All this we want to provide as web apps such that we have better user guidance. So to sum up, before embarking on a machine learning project, the Toolbox supports you to make the right questions at the right time, tailored to your use case. And it helps to picture what your final machine learning system design will look like. Let's take a closer look to the concrete implementation and get a glimpse of the Toolbox. So what you see here are RapidMiner operators. RapidMiner provides a point-and-click graphical box design to implement machine learning analysis. So at the first implementation of the use case, from a data scientist's perspective, we need to create a so-called data schema, which is including all the requirements and properties needed for the specific use case. If you already have the data set needed for the specific use case and the data is already transformed as needed for the following analysis modules, we can just retrieve the data and then apply the create data schema to get a schema which is already including all the properties and requirements needed, such as the attributes needed with the attribute name and a specific description and some other properties. And from Brewer's perspective, he or she already gets the specific data schema and has his own data which might look quite different. For example, it could have different names which need to be renamed for the following analysis modules, and also we need to check if the properties are right. And then in general, you can see which data you need and which you can provide given by the requirements in the data schema. And then for mapping the attributes in the new data set to the schema, we provide a web UI. Then you can see on the left-hand side which data you need for the use case, and on the right-hand side you can select your data which represents those attributes. So for example, you need the temperature, and then you check the description to know better what this temperature is about. So this temperature is the temperature applied in the meshing process. And then you as brewer know, okay, that's called mesh_t in my data, and I can select it here. And after mapping your data to the data schema, you also have to adjust your data to the schema property-wise, and this you can do by applying the adjust data to schema operator, which converts your data by automatically generating sub-processes, which include the renaming, using the mapping you provided by the web UI, setting roles, replace missings, and so on. And then while production, you might validate your running production data against the schema, and doing so, you can detect problems with your data, like missing data or concept drift in the data. The validation results might look like this. So you have a status, which might be valid or fail, and then you have a validation type. So the attribute existing check fail, so some attribute is missing, for example, and you might check the statistics which are specified in the schema, and so on. This is where I hand over again to my colleague Josef. He will tell us some more details about our deployment in the malt yield prediction.
Yeah, thanks, Mina. And that's when I would like to tell you something about our results and the success of this use case. So until we finally figured out how to handle our model, we tried a couple things beforehand. In a pre-study, we modeled with ready available data from our production management system, but majorly on solo batches, meaning we use malt from just one supplier. Based on this, we were able to predict a correlation between the real and the predicted yield with an R-square of 0.8 and with a relative error of 0.6. This was quite a good start for us and was promising enough to carry on with modeling. If you look at the acceptable range, 0.6 might seem large, but it's better than any approaches we tried beforehand. We tried 3 different types of algorithms: a random forest, a generalized linear model, and a decision tree. Considering the runtime, explainability, and the result, we figured that the GLM model worked the best for us. The result was not the only thing we figured out. For our pre-processing, we want to predict malt yields on standard batches. We need the exact same attributes, and we figured out that our malt specifications have the largest impact on our results. So part of the development of our toolbox also was to somehow crack the code to map our malt deliveries through our silos to the brewing batches. For transfer, on one side, it is handy to use the same data schema to implement the use case new production sites. On the other side, the toolbox is also handy when we want to transfer and implement it on new datasets and models, and even use cases on a general approach for the whole beverage industry. Respectively, for this use case, the data schema always stays the same for us. How do we want to deploy such a use case in production? As you might remember, right at the start, I told you that we have a different paradigm environment at the moment. This means that we, the production teams, are kind of forced to work with the materials we get. So in a short term, we want to try to predict the yield to implement a proposition of optimal silo settings for maximum malt yield. Alongside with that, we want to compare predicted yields with the real malt yield to estimate or quantify a monetary benefit. If this succeeds, we actually can tackle the paradigm shift to implement a prediction simulator at the production site to also change recipe and ratio settings at the brew house. In the end, Mina will tell you something about the takeaways of this use case and the toolbox in general.
All right, so what are our takeaways and findings? We have 2 perspectives there. We have the industry side and the data science side. On the industry side, we realize that data amount is not always necessarily the same as the information gain, and that the setup of a data science environment and infrastructure can be more challenging than expected. So that's also one finding which led us to the belief that our toolbox should provide support there. And on data science side, we realize that it can quickly happen if you don't pay attention, that look ahead sneak in. So for example, if we have the multi-prediction, while we have different points in the process line where we collect data at different times in different steps, which reflect the batch flowing through the process line. So consider all the different time data there to evaluate this use case. And also we had other use cases which directly included time series analysis, and there of course you always have to be aware of those issues. And of course in general, make your applications scalable and reusable, and for us it was in particular important to make our use case models reusable for others as well. And then last but not least, the critical factor which makes a difference between success and failure is the ability to collaborate and iterate as a team. So obviously, join your knowledge and check how you can generalize all those gained knowledge to make it reusable for others. And also what we realized is that when creating result dashboards, add to existing reports. So make your visualizations and representations of your data and results as intuitively accessible as you can, and that you can do as we realized by just keep it similar to existing reports and add to those. And also, very important, early data management. So your machine learning model is of no use if there is no data associated. You will likely have training, testing, evaluation, and even prediction data sets. And you might have to answer questions like, how is your training data stored? How large is your data? Also, you might consider this for computing costs later. And how will you retrieve the data for training? How will you retrieve data for prediction? And so on. So think through your data needs as soon as possible so you can make sure your budget can support the model through both training and production. Thanks a lot for listening. If you are interested in more details of our research project, Dablo, please check out our website.